Okay, welcome to our Bucky weekend call on the weekend of 426, 427, depending on what continent you're on. We're studying, we may do something else, but we're studying A Fuller Explanation by Amy Edmondson and learning more about what's going on with Buckminster Fuller. And so I'm not actually sure. I'm going to find out while we're talking what page we're on. But I was gone for a couple of weeks, so you guys got to tell me, where are we? Anybody want to share
Oh,
with me where we're going to start or where you guys left off? Anybody know what page you are in the book? Maybe as we do our shares, we can go from there. And how are you feeling? And what do you anticipate getting out of today?
okay. I'm also trying to figure out how many weeks I didn't miss, I think. Okay. Yeah, I got to check in the book. Um, yeah, okay. I'm actually looking forward to this like the last on Wednesday I shared how Bucky showed up. I felt so strongly Bucky showing up at the TED talk. And it's beginning to make a more impact in my team as well. When I shared recently, I shared with them about the geodesic dome, and I could see them also, at least now that they can see that the things I've been sharing about Bucky, and now is showing up in what's going to impact all of us. So that was really really powerful, and I just want to go continue on this journey to see what else shows up. It's just amazing. I mean, he wrote about all these like 100 years ago he started, right? And more than that. And he wasn't even around anymore by the 80s, and here we are. The things that he created, they're making worldwide impact. So I just, let's see where else we go with this, with Bucky and with all of you. I'm loving every time we meet up. It's just unbelievable for me. Okay, so Richard, how do you feel, and what would you like to take away?
Well, I'm feeling pretty good. We've got a really nice spring day, so that's uh, I'm starting to see some green. And after coming away from Ireland for 2 weeks and saw what emerald green means in Ireland, it was one of one of the really um, nice side benefits of going when we did is that arriving April the 6th, it sort of felt like that was the first day that the the leaves and the blossoms are really starting to come out. And by the time we left in 2 weeks, everything was in full green. uh, but yeah, I mean, I was fascinated with what you said on Wednesday, Anne, um, and it finally kind of sunk in why you were in Vancouver and in Canada. And so I looked up the TED Talk conference, and oh my gosh, I mean, I'm uh, I'm overwhelmed just looking at the agenda that was in front of me. I can only imagine what was going on for you in those number of days. That it was almost like you were bouncing off walls with all kinds of exciting things being spoken about and spoken to, and then to feel uh, sort of Bucky emerging in several different places. Um, so I looked up more of Ariel Ekbom's work and this whole idea of a self-assembling habitat, and um, I mean there's a whole avenue of reading and thinking that um, you've really kind of introduced us to, and I introduced it to the Trim Tab group this morning that meets every 2 weeks, and nobody put up their hand to say that, oh yes, we know who she is, and we know her work, and so I was really able to introduce um, your discovery of her I channeled you into the trim tab message this morning. um, so yeah, that it's really quite exciting, and and the other thing about her self-assembly, um, it brought me back to the experience several years ago when they were trying to put a robot onto the moon, on the surface of the moon, and one of the big dangers is that if they put it in a square box, um, it it would not necessarily land correctly. Uh, so they eventually put it in a tetrahedron box. Um, and so it didn't matter which way it landed, it was always going to be, on a stable sort of landing place. And it was fascinating watching um, that particular moon landing and realize that it was just that simple old minimum system tetrahedron that was getting the robot onto the surface of the moon. So if her work turns out to be something sort of uh, well, similar, I guess, in terms of breaking ground in the frontier of outer space type of travels. Yeah, amazing. I'd like to hear more, but it just I'm just so caught up with what it must have been like for you to be in that environment for the days that you were there. Um, it was just, I mean, the list of people that were speaking was incredible.
Yeah.
So yeah, and and this morning, one of our trim tab people mentioned several weeks ago that he would really like us to get back to synergetics, and he had an idea that we should do a brief reading every 2 weeks. But several years ago, he actually kind of cataloged all of the synergetics volumes, and he cataloged them in such a way that uh, he can extract several lines or half a page um, at a time. And so what he's doing now, we confirmed it this morning, that he's going to send out a brief reading of synergetics every day between our 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 2 week sort of time meetings, and then every time we meet, then we'll pick one of those readings that he'd sent out over the past 2 weeks, and so we're going to try that. And this morning it was really interesting reading about a system, and one of the things that came out of the reading is that uh, Bucky kind of changed his thinking on the language he was using for vertexes and vectors and that sort of thing. So he said that instead of saying a vertex, he uses the language of what event foci, that's sort of the vertex, the corner. And then in terms, instead of saying face or window, he he uses the language of planar facets. And instead of using the word edge or connection, um, he uses the language of wavy linear relations. Um, so that was quite exciting for me, especially the wavy linear part, because it speaks to the nature of the relationship between people or things, but in our case, people, and they're always there's not a straight line. It's a wavy linear kind of line that goes on back and forth between people in their relationships. Um, and more and more as I become um, familiar with the his systems thinking, the more and more I realize that it's the wavy linear sort of activity between events that does the kind of thing that Steve was just talking about. It either, puts you in a place where you overreact, or you react too soon, or you react without thoughtfulness, um, and or you do the kind of thing that, again, you were talking about, Steve, in terms of your sitting for 10 days. Um, that you become more mindful, you become more tuned in to not only yourself but to others, and that has a huge bearing on the nature of the relationship. And so, that the for me, the end result now is becoming more and more that it is the relationship between events, or foci, that really makes the system sort of function well or not so well, or anything in between. Um, so yeah, that's kind of where I'm at. And Steve, how are you feeling, and what's your intentions for today's readings?
Um, Pretty good. I'm feeling good. I want to get clear. You called it event foci, or the vertices, or the
Yeah,
and is one vertex a foci, an event foci?
yeah,
So that means that that one node has multiple aspects to it, because it's a foci. Because
yeah,
focus is singular and foci is plural.
yeah.
Mm.
So
So
that means it can blossom out.
yeah, it can blossom
Mm.
out or
It-
blossom
Right, right.
in, depending
yeah,
on how it's going. And then you said planar facets, and then you said wavy linear what's
relations.
relations. Relations. Okay. Go ahead, Anne, if you had something to say.
Yeah, no, this planar facet, then what are they? I can't how do you relate that then?
It's a
Planar
window.
facet.
It's the window or a side of a tetrahedron.
Yeah, but so like just now you put it very nicely. The foci means that like it's not one, there's more, right? So what is the change now looking at the window or the surface into this planar what? Facet, yeah.
Is it facets plural or facets singular?
It's facets plural because
Yeah,
there's four of them.
there's,
Mm.
I
Um,
see.
and
Is
and
one window a facet, or is one window a facets? Because each
I
window
take
has
one
three edges.
I take one window to be a facet,
Okay,
a
cool.
face.
Yeah.
And
Okay.
then the big difference that I've been picking up over the years is that the difference between a platonic solid, is that the face is opaque. You can't see through it. And what I have been doing is, I call it a wireframe tetrahedron.
Yeah.
So now the windows are open, uh,
Mm.
and so you can actually see the edges, or the wavy linear part, more clearly, um, and the facets in that sense take kind of a back seat. Um, Although one of the things that happens for me in working with children and foster parents and blended families, um, we worked with the idea that one of the things that the blended family has to be able to do is that they have to have a triangle that still involves the other parent and the children and the new parent. Um, and then there has to be a window for the children and their present parent. Um, and then there has to be a window that includes the new parents, if you want, and all the children. And what it was doing for me was helping people say, you've got to realize that, um, there's a time for each one of those windows to be important, and the rest of you stay out. Um, let them let them have their time together. and then there's a time for the whole new family to be together, and you would probably want to say to the others, this is not your time, just wait. Uh, and it was a very helpful way uh, to respect the several different kinds of family interactions that needed to be respected in the emerging of two families into a blended family.
Gee, I think that's just so important. Because it's so easy. You know, in a circle, in our Native American stuff, we use a talking stick
Mm-hmm.
so that each person gets a talking stick. That's their time. Everybody else shuts up.
Yeah.
But the idea that there are multiple people involved and each of those multiples have a separate facet, and so each facet needs its own time is
Mm-hmm.
kind of important because it's so easy to leave. You've got more than a bow tie there. You've got
Yeah.
a tetrahedron. And and every one of those interrelationships need some time
Mm-hmm.
and evaluation and awareness. Yeah, really powerful. Woo, very complicated or very complex.
Right. Um, and yet
I
very
can make it
simple,
complicated. Yeah.
and yet very simple in getting across, again to the kids or another person saying, look, we're not disrespecting you. It just doesn't happen to be your time. This is somebody else's window. So please sit back, and your window is coming up, an hour from now or tomorrow or next week. But you're not going to be ignored and left out. Your window is important. And yeah.
Cool. Anne, are you complete with your questions on
Yeah,
Richard's share?
yeah.
And so the other thing, Richard, talked about platonic solids being more a platonic framework because they're translucent, actually. At least the structures are
Yeah.
translucent because
Yeah.
they're just energy is what they are. And cool. Well, cool. Thank you for sharing that. Now,
And your turn as well.
yeah, my turn. And so I'm feeling really good. I'm back from my 2 week thing. I'm still not in the flow like I'd like. I'm um, there. I had a clock and I had to be up at 4:30, and I didn't have to be up at the 4:30 in the morning, but I chose to do that 7 days out of the 9 days, or 8 days out of the 10, I was up at 4:30. But I had one night that was real tough because I didn't sleep at all. So I didn't wake up at 4:30. I waited until 7:40 before I woke up. So, but it's a real challenge. And and I'm still sorting out from it all. So I'm glad to be kind of back in the saddle. I'm looking forward maybe to this call, maybe grounding me a little bit more into what's on my desk. I haven't even finished my emails yet. You know, I got probably 12 days worth of emails, and I've been through this last 7 days doing what I can to plunk through them, and I'm not through them at all. I found some very interesting stuff, and I don't like to just, I want to do the stuff as it comes on the table. So I'm just adjusting in and feeling really good about tonight's practice. Has anybody, and I'm concerned about Joe because he was on the call at the beginning, then suddenly said he had to leave, and it sounded to me like an emergency, and he was driving his car. So
And
maybe,
there were a lot of lights, blue lights, red lights, white lights
yeah,
flashing.
it was at night in the car he's
Uh,
driving. So back there it's 11:30 his time.
mm,
So PM. So I don't know. What are you discovering there, Richard? You were gone for 2 weeks, so I wonder if anybody did anything for the last 2 weeks, and Joe was probably the guy who knew what happened.
Yeah.
yeah, we did. I think we did have a meeting, and I think Manu joined us, three of us. You
Oh,
know, yeah. Let me just
well,
get my. I just
I
left my.
have cool, and I have us left off at page 128 is where I have us left off. So um, we can I'll go to page 128 right here, and then as we learn what's going on, why we will And I'm going to go over my phone and see if I can text Joe and see what's going on. I'll sit and we'll see I'll kind of wait for it. In fact, I think I'm going to put the machine on pause until we decide what we're going to do so the recording doesn't get too discombobulated. I'm putting the recording on pause for a moment. So go ahead and talk about whatever you want to do.
Okay, let me see. Let me look for it. I know we were somewhere.
I think what's up might be quite close to where we were, because I have some notes on figure 8.6 and 8.8, and there we are at 8.11.
I think I've got it up to 8.12.
Oh, okay.
And I think we were about to go into vector equilibrium, I think.
Right.
Yeah.
So you got 8.12, and the text part would be either vector equilibrium or frequency.
Yeah, it says vector equilibrium.
What page are you? What
and
page
then
are you on?
frequency after that. Page 129.
Okay,
yeah, because
good,
we were at the yes, no, yes thingy. Yeah, that day.
okay, because I had us at 128 before I left. And
Mm.
I will go to the next page here. There we go. Oh, geez. Okay, page down. Okay, there we go. Closest packing. Wow, that's very interesting that it's moving so slowly. Okay, so you think we've done the yes, yes, no, yes, yes, no? That does
Yeah.
sound familiar. I remember us, well, we'll go ahead and maybe everybody else is as disjointed as I am about this. So, oh, I thought I paused the recording. I didn't. So there we go. Okay, so I remember that we had every 3 sets has a center ball. I do remember that. The top is a center ball, then 1, 2, 3 center ball. 1, 2, 3. I do remember that. And that's what the yes, no, no, yes is. Yes, a center
Oh,
ball,
right.
2 no's, no center ball in less layers. Next layers in 6 frequency tetrahedral spheres backing. So you think we've read this about the yes, yes, no, no? And
Yeah.
we're going to start at vector equilibrium then. Okay, really good. I'll start and read a couple and then we'll go from there. Is my screen moving? Do you see vector equilibrium there?
No, it's still sitting on 8.11.
All right, then I'm going to stop sharing and I'm going to reshare. Wow, that's very interesting. Okay. Oh, I don't think I stopped sharing. All right, there I stopped sharing and I'm going to reshare. I don't know why it would be giving me such a problem. Okay. Boy, that's interesting. Oh, vector
Yep.
equilibrium. Let's hope this page is on time. Vectoring, I'll start to read. Vector equilibrium. In cubic packing, 12 spheres surround one sphere, with each sphere tangent to every neighbor and without any gaps. The perfect geometric fit of the 13 omnisymmetrical forms provides a basis for understanding the fundamental directions inherent in space. But we saw that the configuration is more specific than just a numerical consistency. The spheres outline the vertices of the cube octahedron, or VE. Okay, good. It did change. This shape seems to appear out of nowhere, created by the cluster of cornerless spheres shoved together. This result is a counterintuitive as it is reliable, is as counterintuitive as it is reliable. The more we learn about the shape of space, however, the more natural the appearance of the VE, or any manifestation of 12 degrees of freedom. So that's where the 12 degrees of freedom come from those 12 spheres. That's interesting. Okay. Frequency. The six squares and 8 triangles outlined by the close packed spheres, although unmistakable even in the simplest case, become more and more distinct as the frequency increases. Good. I think here comes Joe. Okay.
Morning and
Hey, welcome back, Joe. Is everything okay, my friend?
yes, yes. I was just shocked by a little bit by something. So uh, anyway, I'm back.
Okay, good. Would you like to share? We're just starting to read here about frequency in close packing spheres in the cube octahedron cluster. Do you want to share how you're feeling and what you anticipate today? Or is it you want to wait until you land on your computer?
Um, yeah, I'll just share really quickly. I'm feeling fine. I actually had a pretty good day, with the exception of a couple things. But yeah, I mean it's I think I'm getting to a point where I accept things the way they are. So that's really cool. And so
Wow.
from that perspective is I'm just,
Actually, that's quite the human achievement is to accept things the way they are, Joe. I think that's pretty huge.
it is, it is. It's at peace with what's goes on around me. That's all.
Wonderful
So,
for you.
so anyway, that's all. That's my check-in.
Okay, good. And so we're going to read along here. And
Joe,
Yes.
Joe, I shared that we were at vector equilibrium and frequency. It's about right, where we stopped after the
Uh,
yes, no thing.
I what was that? I believe I have to check. I did highlight the section that we left off. But I'm trying to close. Can I see? Can you pull up, Steve? Actually,
yeah, it's actually we're on page 129 is where we started. And here it is. And now we're down to um,
So we just read, Steve just read vector equilibrium, and now we're at frequency. I think this is about right, yeah?
yeah. I mean, we
Mm.
definitely were talking about frequency last time.
Mm. Okay.
And so that I do remember. And there was the section that we were waiting to cover, and I think with a group. So I think that sounds right.
okay, cool.
Okay.
I'm just going to start reading again. The 6
Okay.
squares and 8 triangles outlined by the close packed spheres, although unmistakable even in the simplest case, become more and more distinct as the frequency increases, as Fuller's convention is to refer to the number of spaces rather than spheres along the, quote, edge, quote, of the cuboctahedral cluster as the frequency of the system. The first 12 around one group is one frequency. The next layer, in the VE case, a surrounding envelope rather than just another layer added to the bottom, is two frequency, having 3 balls along each edge. The next is 3 frequency with 4 balls along each edge, and so on. It follows that the higher the frequency, the smaller as individual spheres in a relationship to its polyhedral face, and so these polyhedral faces look progressively less lumpy or more sharply defined. Refer to figure 813, which is below. So those are looking less lumpy.
Bumpy.
Okay. Geez, and I just read less lumpy. Okay, there it is, less lumpy, or more sharply defined on figure 813, and of course there's figure 813. The precise planar organization of the clustered spheres becomes more obvious as the frequency increases. The appearance of 8 triangles and 6 squares was not an accidental property of the first layer. The VE is here to stay. The lesson is continually reinforced by additional layers. So I guess A is a cube octahedron, B is a cube octahedron, and C is a cube octahedron, if I'm reading that correctly.
Yeah.
Okay, having the shape of symmetrical nuclear, whoops, I went too far. Having established the shape of symmetrical nuclear sphere packing, we proceed to investigate numbers. 12 balls fit tightly around 1. How many does it take to completely surround the 12 with a second layer? By carefully placing balls in the nests on the cluster surface, we generate a 2-frequency VE shell of exactly 24 balls. We might begin by placing 1 ball at the center of each of the 6 squares and then in each nest along the 24 VE edges, thereby superimposing 6 2-frequency squares, 9 balls each, over the simple 4-ball squares, figure 813b. The edges of the 6 2-frequency squares supply the spheres for the adjacent 2-frequency triangles without adding any more balls. These 2-layer triangles cover the 8 3-ball triangles of the first layer. The 12 vertices, or corner spheres, are each shared by 2 squares, and so 12 must be subtracted from 54, 9 spheres per square times 6 squares, to get the total number for the second VE of 42 spheres, again referring back to 3E, or to 813. So this is it here. So if we had a video, it would go from here to here by adding the balls described. Although I understand the concept, I'm not actually seeing that transition visually. Does anybody else want to comment on that? These are all octahedra, if I see it correctly. A cube octahedra. These are all cube octahedron. Okay, I don't hear anybody protesting. Somebody else want to read from envelope?
I'll be on in my computer in a minute, but I actually can read from my phone.
Well, it's up to you and what you want to accomplish
Are you
here.
driving?
No, I'm
Are
not.
you still driving?
I just pulled in.
Okay.
But I'll be on my computer in a moment. But I can read the next paragraph.
Okay. All right.
Actually, this might be a little harder than I thought. Envelop the whole package with a third layer, a 3-frequency shell with 4 balls per edge. Following the above procedure, we count 16 balls in each of the 6 squares for a total of 16 times 6 equals 96, from which we must subtract the 12 vertices counted twice due to overlap between squares. The edges of the 8 triangles are again already in place, provided by the edges of the squares. But on this shell, a central sphere, which belongs in each 3-frequency triangle, must still be added. 8 more spheres are therefore needed to complete the enveloping, I can't see, layer at 96 minus 12, 8 yields a total of 92 balls. The next shell 4-frequency requires 162 balls. The 5-frequency layer consists of 252. Is that 6?
Yeah.
Is that a 6? Is that negative?
I don't know, Joe,
Uh,
because up here it says 96 minus 12. I don't know. I don't know what that is, Joe.
Yeah. The minus 12 is the edges that you know, that the edges that what's that? It's the square and the triangle. So it's already accounted for. So they,
Yeah.
if you look at the triangle, they remove the 12 balls, and then they added 8 because of the ones that have not been counted inside the triangles. Does that make sense?
It does.
If you look
and
at
now
because the squares are adjacent to the triangles, right? So that the vector, is it the vector? Yeah, the edge is already accounted for when you calculate the squares, so you don't count it again when you calculate the triangle. That's what the minus 12 is.
okay.
Does that make sense?
I'm gonna shoot.
If you go back to the
That's what I was trying to do, was go back to the,
18.3, yeah.
I was trying to go back to there. And
I guess I was that 6 minus? I don't know. I can't. It's very
I
hard.
don't know, it looks like 6 minus, but I don't understand that. Whoa, 131. Okay, it's the next page, sorry. Page up, there we go. Now we come down. Come down. Wow, there's 131 again. That is so amazing to me.
Yeah, because
Page
if you can
up.
get to the
And now VE 12 layers second. I'm still on the, I have to go one more. There we go. Oh, 12 layers second, page up. Okay, there we go. So this is Anne was talking about this triangle right here. And this triangle right here.
yeah, because if you look at the edges, they've already been accounted for. So left the ball in the middle of the triangle. So since there are about, I think it's 8 triangles, so they added 8. If you look at C, right? So there are 16 balls in the square, and so the edges with the triangle, it's already sharing, and therefore it's been accounted for, and so they remove the 12, and then they added in the the ball in the middle, and there are 8, I think, triangles.
Right.
That was a really good, very clear way
I think
of describing.
we're stuck.
Yeah.
Minus 12 plus 8.
Right. Okay. Okay, we left off right here, the next shell with the 6 minus thing. And then here's the next sentence.
6 minus of 362 and so on. We are now able to detect a pattern by looking carefully at these numbers: 12, 42, 92, 162, 252, 362. It will come as no surprise to the observant student of numbers to learn that the next shell consists of 492 balls. What exactly is going on? To begin, we notice the consistent last digit. Every single number ends with 2, reminiscent of Euler's law and its constant 2. Fuller interprets this persistent excess of 2 and radial sphere packing as further affirmation of the inevitable poles of spinability. Actually, this is something that Minute refers to quite often. Inherent in the topology of singly closed systems. Sorry. And indeed, the temptation to embrace a single explanation is strong. The fact that the number of spheres per shell always ends with digit 2, even though those numbers increase drastically with each successive layer, seems strange to ignore. we want an explanation for nature's behavior. But at this stage, speculation as to significance is a sidetrack. Our task is to fully describe the configurations. As soon as we fully understand the patterns and thus armed with the facts, such speculation will be appropriate and indeed inevitable.
All righty, we're on to page 132. And there we are. Do you want to go in the house, Joe, or you want to keep reading?
Yeah, I'll keep reading for a moment, just another moment, and then I'll head into the house. After observing the reliable last digit, we can simplify our sequence following Fuller's procedure by subtracting the 2 from each term, removing the distraction to assist further analysis. Sorry, I have a cracked screen on top of that. We are left with 10, 40, 90, 160, 250, 360, 490, all divisible by 10. So let's divide by 10. This leaves 1, 4, 9, 16, 25, 36, 49, and now the pattern is clear. The latter sequence is generated by f squared, for f equals 1, 2, 3, 4, 5, 6, 7. We choose f in this case to represent frequency, for it turns out that the relationship between frequency and number of units per shell can be directly specified. Oh, you know what? All right, yeah, now my battery's dying. So this is actually getting to be a fun challenge. Nature thus reveals, yet another generalized principle. This equation actually describes a straightforward edge length to surface area relationship, exactly what we expect from geometry in a slightly different format. Did I say? Yeah, I started at the right place there.
Yeah.
Directly specified. Yep. Then the next question is how to specify the relationship in precise terms. We work in reverse from our final sequence, f equals 1, 2, 3, 4, to generate the original sequence. First, we must raise the frequency f to the second power, then multiply each term by 10, and then add 2. 10f squared plus 2 therefore gives us the total number of spheres for any shell specified by frequency in nuclear sphere packings.
Wow. Wow, that's interesting.
It is interesting.
I barely followed the logic getting here, but once I'm here, here's your layers, 1, 2, 3, 4. So all you got to do is just 10 times that, square it and add 2. 10 times f squared. So 16 times 10 is 160 plus 2 is 162. And that's the number right there. Because this is the fourth sequence. Somehow I'm getting this. Is anybody else getting it?
Yep.
Yeah, it's actually, the second part I definitely got, but the first part,
Yeah.
a little bit, probably something I should revisit. Oh wow. So
Very cool.
okay.
Do you wanna get in your house before your battery quits, Joe?
Yeah, I do, because literally it's just gave me another signal.
You
All
betcha.
right.
Cool. All right, we'll continue and see you in a few minutes.
See you in a few minutes.
Anybody want to read here? Richard or Anne?
Yep, I'm back.
Okay.
Just not turning the camera on, that's all.
Okay.
Quite poor.
Do you
Oh,
wanna-
wait, I'll
do you
turn
wanna
off the
read?
camera.
Okay. Richard, you seem really engrossed over there.
Well, I'm
I think
looking
my
at
line
that.
is
Your wedding?
Richard.
I didn't hear you, Richard. What did you say?
Well, I've got the book in front of me as well.
Okay, so you're just over there studying the words. Very cool. And did you want to read? I thought you kind of wanted to read, Anne, but
No, I think my line is not stable enough to read though.
okay, very cool. Richard, do you want to read or shall
Mm.
I read until Joe comes back?
No, I can
Okay, good.
read.
We're at icosahedron.
Icosahedron. We return to the initial 12 around one cluster to try a new twist, literally. Imagine that we have 13 spherical balloons instead of ping pong balls so that we can reach through with a long pin to puncture the nuclear balloon, causing it to slowly deflate. As the nuclear balloon disappears, the 12 outside balloons shift, closing in symmetrically toward the empty space in the center. They can't go far, only enough for the 6 unstable squares of the VE to tighten up into 2 non-coplanar or hinged triangles. Squares were stable in the VE only because the nuclear sphere held them in place. The array was thus stabilized by triangulation in radial directions, producing alternating tetrahedra and 1/2 octahedra. Now, without the nucleus, the surface must be stable by itself. It therefore must be triangulated. Figure A14.
Which is on the next page.
Right.
So if you want to read this paragraph, I'll switch over to there.
Yeah, the VE configuration has 12 vertex spheres. What shape do these 12 spheres become when fully triangulated? The 6 squares transform into 2 triangles each, which in brackets added to the original 8, make 20 triangles in all. 20 triangles and 12 vertices.
Question mark.
Yeah, this is none other than our friend the icosahedron, the largest of the regular polyhedra, one of the 3 prime structural systems in universe. We can create higher frequency versions of the icosahedron, but there will always be single layer shells. The icosahedral configuration arose as a result of removing the VE nucleus. The remaining spheres move in, partially filling the gap, and thus their positions no longer allow a space-filling array of spheres. Because icosahedral clusters are completely triangulated, they cannot be extended either inwardly or outwardly. They lack the necessary alternation of tetrahedron and octahedron.
Okay. And so here is there's the caption on that illustration.
Yeah, what I always like about the icosahedron and its 20 triangles is the shape, of course, that Bucky used to lay down flat to build the Dymaxion map. So it's on a planar scale, it's 20 triangles laid out to accommodate the one island, what is it? One island, one ocean world map.
Yeah. Yeah, and so it goes back and forth between the cube octahedron, or at least in this case, it goes from the cube octahedron. When you take out that center ball, it collapses to an icosahedron. That's what I'm hearing, right?
Yeah, and that's where I've sometimes have had my own trouble
Yeah.
understanding whether it's the icosahedron dropping into the vector equilibrium or it's the vector equilibrium that drops into the icosahedron.
Well, when Bucky starts his jitterbug, he starts with the cube octahedron, and so then as it drops down and twists, it collapses into the icosahedron.
Yeah,
And what has effectively happened is that center ball gets removed, the center sphere gets removed.
and And that means if I've got it right, the squares disappear and you end up with nothing but
All
triangles.
triangles, just because of that one central sphere is removed. Any other comments, questions, musings? Shall we stare at it a little bit longer? Will it reveal itself to us, or should we continue reading?
Well, if again, now if you've got the vector equilibrium, like a physical model of it,
Right.
then you push the vector equilibrium down and twist it, you'll
Yeah.
end up with the octahedron. And then when you kind of lift it up and turn it, torque it down some more, you end up with the tetrahedron, and you can then move it down to basically a several layered triangle. And of course, if you let go of it, it'll pop all the way back up into the icosahedron.
The cube octahedron.
Or cube
Right.
octahedron, yeah.
Yeah. Okay. Any other comments, questions, musings?
Well, I just this has to do with the tetrahedron. I might have explained this before, but I was passing a tetrahedron model around an audience, a circle of about 60 people at a conference, and I was displaying the tetrahedron model, which was made up of dowels and elastics, and so it had flexibility. And I always used to say to people when I handed it around, I said, just handle it, feel it, see whether it says anything to you, communicates anything. And most people, it didn't say anything to them, and they just passed it on to the next person. But sometimes they talked about it. It says it's flexible, or it's firm, or it's stable. Anyway, I got around to one fellow, and for some reason, um, he took offense, I guess, at what I was doing. And so when he got the model and it was in his hands, and I said, "So what does it say to you?" Um, and he dropped it on the floor and said, "It doesn't say anything to me. It just says it's terrible." And he stamped on it, and the thing just collapsed down flat. And of course, the audience saw him, destroy my model. And they were horrified because it was like they were treating me as the guest who was presenting. Um, and so he was a little shocked too. And so he took his foot off and the thing backed up, popped back up into its full shape.
Yeah.
So his embarrassment was saved really in terms of the recovery of the model.
He became the teacher of the moment,
Yeah,
and he found out how indestructible the universe was.
yeah,
I have a little diagram kind of showing what you just talked about. And I've gone and I actually transcripted the Jitterbug uh, YouTube thing. And here are the shapes that it goes down through as it collapses from the cube octahedron into the icosahedron, then collapses down into the octahedron, and then collapses down even further. And this is where it went flat, I think, that you talked about.
yeah.
It popped back up to this and scared the poop out of him. And here are some full color renditions of the vector equilibrium and describing that. And I thought this paper, and somewhere in this paper, I've actually have a transcription of Bucky's whole speech. I'm really surprised it's not on page 2 here, but that's interesting. Cool. So we got down to single thickness, I think, right? And then the next paragraph is here, or have I lost the place? I think that's where we are. Do you want to
Yeah.
continue reading from there? Richard,
Yeah.
please.
What will happen to the relationship between frequency and number of spheres on a given shell? Well, it turns out that while both shape and volume change considerably, the number is unaffected by this transition from the VE's 14 faces to the 20 icosahedral triangles. We verify this fact through the following observations. Notice in figure 8.15 that a square pattern of spheres can be compressed into a rhomboid diamond shape without changing the number of spheres. The resulting diamond is more tightly packed than the square and consists of two triangles on the same frequency.
As the
As the
original
original
square.
square sharing one edge. That is the row of spheres that used to
Whoop. Sorry. Okay, good.
that is the row of spheres that used to form the diagonal of the square, 815, shows how the spheres of two triangles on an icosahedral shell correspond to one square face of a VE on the same frequency. And therefore, because the spheres on an icosahedral shell are all as closely packed as possible, as opposed to the VE, which alternates triangles with the more loosely packed square faces, a smaller, denser shell is produced with the same number of spheres as the VE shell of the same frequency, 10F squared plus 2, therefore also applies to icosahedron.
This explains how it goes flat. And he calls this, I think, this is a hinged diamond, which has two triangles to it. Here's one triangle over here, and here's another triangle here. This is the diamond in the icosahedron, and they're hinged.
And that gives you that rhomboidal
right.
shape.
So when these balls roll into the nest, they go like this, and they create a triangular shape instead of a rectangular shape. Okay, good. Joe, we just saw the universe being created, and you missed out on the whole thing. So
yeah.
Good luck. We're on page 134. If you have your book.
Yeah,
right
that's
there.
a pretty big miss.
Yeah.
What I like about the diamond, if you turn that rhomboidal structure just upright, turn it 1/4.
Yeah.
You now have the diamond with the two triangles in a hinge form. But if you connect the top and the bottom, then you've actually created a tetrahedron.
Yeah. The thing that you missed that was the big revelation for me, Joe, which you can catch, is was this thing. That when what makes the difference between the vector equilibrium and the icosahedron is the middle ball goes out, the middle sphere, that black middle sphere, when it drops out of the cube octahedron, because that space is missing, everything falls together like in the diamond diagram below, and you go from a cube octahedron with the squares to an icosahedron with all triangles.
Wow.
And it's all by taking out that ball, that one sphere. And she explains that, the part we just got to, that's what's explained right here. It goes from the square configuration here. When the center ball of this cube octahedron is removed, it goes flat. And all the spheres nest with each other instead of rectangulate. They triangulate.
Okay.
And that's how and I kind of shared Bucky's jitterbug, as it goes from the cube octahedron, starts to squish down, and
Right.
then it goes into the icosahedron, and then squishes down further into the octahedron, and then goes down flat. And Richard told his story about the guy in his seminar who just was totally unimpressed and stomped on Richard's model. And everybody was shocked because Richard was now insulted. He was the guest speaker, and the guy broke his model. And when he took his foot off, it popped back up into a cube octahedron and actually proved Richard's point. So the villain became the hero.
Yeah.
So anyway, but the key to that is that center sphere. When it goes away, the rectangular spheres triangulate into the icosahedron. That's what I said by missing the center of the universe, the creation of the universe.
Interesting.
Okay, guys, I'm gonna have to go. I'm so sorry. I'll
No
catch
worries.
you the
Why
next
don't you
meeting.
take a
Yeah?
second, and do you have time to share what your takeaway, any takeaways, or you got to run?
Oh, sure. Okay, sure. Yeah, actually, every time we start the meeting, and then we start reading. Okay, you know what? Now I'm gonna have to connect all over again, right? But it's very strange. I find it very strange because um as we go in, and then the things that we talked about just the week before, or before that, and then it connects back again, so that wasn't how school was before. Whatever we learned last week, this week you can't even link it, right? And the way the whole explanation is laid out, it actually adds on. And even if you look at the formula or the explanation, it doesn't make sense at the beginning of the meat, and then as we continue reading, it starts to connect back. Yeah. So there's the repetition depth and yet not. Yeah. So that's one of the biggest things that I realize about the way Bucky writes and the way this Amy has actually put forth Bucky to us. And this whole idea of close packing, thank you for taking the time and the space to like really dig down to exactly what is being said. Yeah. Because the words are words, and you can't automatically just see it in your head, right? But every time we meet, we really take the trouble to dig in, to see exactly what it is that Amy or Bucky is saying. So, yep, thank you very much. I thoroughly appreciate all of you. Okay.
Thank you, Anne.
Yeah.
Thank you, Anne.
Cool.
So I'll see y'all next. Enjoy
See you
the
next-
rest of the session. Bye.
We will
Bye-bye.
have a good day.
Will do. Thanks.
You bet. Okay. My mind is blown. So we just read about this figure 815, square pattern spheres compressed into a rhomboid shape. And I've learned the word nesting. So these spheres kind of roll down and nest on each other, which is really nice. And Richard, were you reading? And do you want to continue, or shall I read for a bit? All right, good. You just pointed to me. I couldn't hear you. You got your mute off. The icosahedron contains as much interior volume relative to surface area as is possible with only one type of face. See, this is the part I'm not understanding, and I have made a note for my takeaways here to ponder. Ever economical nature, therefore, chooses icosahedral symmetry for the construction of a shell made of identical units, requiring a minimum of effort. This arrangement can arise automatically. Maximum volume, minimum material. It is thus easy to account for the icosahedral symmetry detected in the isometric virus capsid, the tough protein shell created by nature to house and protect the more fragile genetic material within, which is the source of the virus's instructions. And she gives a a footnote for that. Nature constantly exhibits elegant solutions to design problems because she finds the most efficient and least energetic way to operate. She has no choice but to adhere to the constraints of space. The example of this spherical virus shell is worth our brief attention, for it provides an elegant illustration of the design science of nature at work. Let's examine the criteria. 1. A container must be constructed out of a large number of identical constituents, protein molecules. 2. For reasons which will be explained below, the shell must be able to self-assemble. Oh, it's too
Wow.
bad Anna's not here to hear that.
Really?
Yeah. That is build and rebuild itself automatically.
Wow.
It self-assembles because it rolls into nesting, I suppose. 3, maximum symmetry is advantageous to minimize the energy required for attractive bonds between the capsid molecules. And 4, the arrangement must be stable, which means triangulated. Any comments or questions before I read on?
No, I mean, I'm
Well,
just processing. Oh, go ahead, Richard.
Richard,
well,
did you?
that particular read seems to speak directly to the woman that the architect that she introduced us to through the TED Talks, that
Yeah,
Ariel Ekbloff, and the whole idea of self-assembling habitat in outer space.
yeah.
Interesting.
Wow. Yeah. Okay. The elegance of the relationship between what's that?
No, I was just going to say, can you put that TED Talk in the chat?
Can you put that TED Talk in the chat, Richard, while I'm reading?
No, I mean, I haven't seen the actual TED Talk. I just saw the brochure that was.
I think I saw the TED Talk,
Oh,
or at
did
least I
you?
found the link. I will on self-assembly. When next time somebody else is reading, I'll go looking for it, okay?
Yeah, I appreciate that.
Yeah. All right. The elegance of the relationship between structure and function is well documented in modern biology, and the isometric virus is no exception. Its structure must be suited to its specific functions. A tough shell is to completely enclose minute amounts of genetic material, quantities necessarily insufficient for carrying detailed bonding instructions, yet it must easily disassemble and reassemble itself in order to release the viral genetic material into its host cell. The overall structure must therefore be dictated by properties of the subunits and by the constraints of the space itself. Both critical also establishing a built-in check system. You know, this sounds a lot like I was listening to a podcast or a talk with the IAI, and the guy was speaking. Anyway, he was talking about RNA and DNA
Hmm.
and how the DNA, the RNA, how the DNA instructs proteins and how the proteins relate back to the DNA and to the RNA. And this sounds so much like that conversation right here. I wish I knew more about it and could be specific. A sphere which maximizes the volume to surface area ratio is the key to an efficient solution. Interconnected molecules, which can only approximate that theoretical sphere, will achieve a spherical distribution most efficiently through icosahedral symmetry. Observations of isometric viruses have consistently revealed icosahedral patterns, thus reconfirming that nature chooses optimal designs. She has a footnote there, and it's physical principles in the construction of regular viruses. We shall study the configuration in more detail in chapter 15. And I wish we were talking about DNA and RNA here, not just viruses. I wish we were talking about proteins as well, because some of the animations on how proteins work boggles my freaking mind. Good. Does somebody else want to read?
Sure. I mean,
Okay. Whoops, I went too far, sorry.
no worries.
There you go.
Further discovery nests. Throughout our investigation, we note the recurrence of a limited inventory of polyhedral shapes. This is perhaps revealed most dramatically by the behavior of closed-back spheres. A striking example is found in the results of an extra sphere placed in the central nest of flat triangular clusters. The first case is already quite familiar. A sphere placed in the minimum triangle of 3 spheres produces a regular tetrahedron, assuming all 4 spheres are the same size. A half octahedron is born out of a sphere nesting in a square group of 4 spheres, and we might reproduce any number of familiar shapes by putting
Equiradials.
Or equidarius. Thank you.
Balls
Together. But here we confine ourselves to the triangular clusters, for the scientific method tells us that the strength of an experiment often rests in drawing boundaries. Results thus obtained may lead to broader generalizations about related questions. Remember our observation that every n in Fuller's YNN pattern represents a layer with a nest. Since a triangular cluster without a central ball has a central nest, the center of a ball added to the first becomes the 4th vertex of a rectangular tetrahedron. The next group, 6 balls, also has a central nest. Oh,
Did I just screw it up?
yeah, a little bit.
Keep
going down.
Hey
down,
everyone, welcome to
down.
Space Group, and today we're
where are we? Sorry,
Down.
I was making notes.
That's all right. Go down.
Go down? Okay, good. I think
down.
I must be on the wrong page.
You are. Keep going down.
Okay. Yeah, because we read that footnote 4 and we read here, we're on the next page. There we go.
Correct. Yep. Here we are.
And there's the yes, yes, no, or the yes, no, no.
Yeah. We were at the 6 balls central nest of the 7th ball. Wait a minute. The center of the ball added in first nest becomes. We're at the 6th. That was the 6 balls. That wasn't a significant symmetry.
Well, we could start right just from remember again if you want, because I'm having trouble understanding this anyway.
Yeah. But I was actually following pretty good on that. Anyway, the center of a ball added to the first nest becomes the 4th vertex of a rectangular tetrahedron. The next group, 6 balls, also has a central nest. This is where we left off. So a 7th ball is put in the space. Magically, the shape thus created is a significant one. The semi-symmetrical tetrahedral pyramid, which is exactly 1/8 of the regular octahedron, figure 816. To understand what it is meant by 1/8 of an octahedron, imagine that we slice a regular octahedron made out of firm cheese. To use one of Bucky's images, in half, creating 2 square based pyramids, Egyptian style. Then cut both halves into quarters to get 8 octants, each with an equilateral triangle base, and 3 isosceles. Yeah, sorry about that. Isosceles triangle side faces 45, 90 degrees. The octahedral central angle is 90 degrees. a fact which will prove especially significant in the next chapter. The seventh ball is simply placed in the nest of the sixth ball, triangular layer, to complete the four vertices of an octant. Nothing in our sphere packing investigation thus far would lead us to predict the appearance of this important shape, which is already a significant part of our polyhedral inventory. Such unpredictability is getting to be a pattern. So we proceed to the next case. The 10-ball triangle has nucleus 1, yes, 2, 3, no, 6, no, 10, yes, and therefore no nest. So we skip to the 15th ball cluster, and as before, drop a 16th ball in the central nest. We are no longer surprised to discover that the resulting shallow pyramid is also a very special shape. 1/4 of a regular tetrahedron, a portion encompassing the volume from the tetrahedron center of gravity out to any one of its four faces. The tetrahedron central angle, 109.47. I'm looking forward to 816. Degrees, 109 degrees, 2816, seems so irregular that the sense of coincidence is underlined.
Pyramids formed by triangular number layers plus one ball in the center nest. Okay.
Is that kind of, I mean, that was what we were just covering above.
Yeah.
And so, yeah. Okay. Now she's breaking it down a little bit.
Yeah.
With 15 balls in the plane and 16 in the center, this pyramid is quite shallow. And in fact, as a section of the minimum system, it is Fuller's terminal case. For each of the first 5 triangular numbers without nuclei, a sphere placed in the central nest forms an important shape in the vector equilibrium octet framework, an idea that we shall explore in greater detail in the next chapter. We thus have come to the end of this particular experiment with the conclusion that closed-back spheres automatically yield many significant geometric shapes. Interprocessing, the essence of precession to Fuller, is 90 degrees. And indeed, the counterintuitive or mysterious thing about the behavior of gyroscopes and other examples of precession in physics is the resultant motion in a direction 90 degrees away from that of an applied force. For example, if a downward force is imposed at the north point of a gyroscope spinning clockwise, it will tilt toward the east 90 degrees away from the direction one intuitively expects. Fuller's interprocessing involves 2 systems processing together, which he uses to mean or oriented at 90 degrees with respect to each other. In his sphere packing studies, interprocessing reveals subtle facets of symmetry which might otherwise go unnoticed.
Yeah, I'm having a revelation here on angular momentum.
I was thinking that, I wanted to say that.
What's that?
I was thinking the same thing, but if you say it afterwards, it's.
And at my retreat, I actually had a vision of the creation of planets and how when the sun exploded, or whatever that nebula was that left the cloud out of which the sun was there, things were spinning, and they were spinning around several centers of gravity. And whether they collected mass or not, including the sun and the planets, depended on the spin of the mass, how fast the spin was. And immediately came to my mind a gyroscope, that each of the planets in the solar system maintained their integrity because they were spinning like a gyroscope. And so they maintained a 90-degree relationship with the sun. And then I actually, out of nowhere, I suddenly saw an ice skater who was doing a spin, and their arm was extended out. And as they brought their arm in, they spin faster and faster and faster. And when they brought their arms in, so they had no extraneous mass, they're spinning at the most, and to slow down, they just stick out their arm. And I had this huge vision on gyroscopes, angular momentum, and the creation of the planets. And this whole thing here about interprocessing is describing how these planets spin and rotate on each other. I have something else to say. I'll say it towards the end, but this blew me away. Is there anything else that you guys want to comment on, or shall we continue to the next page? I'm ready for you.
No, I mean, no, I think we're just getting into obviously the essence of procession, and it's
Yeah.
actually become a little bit more clear.
And notice how, I mean, the 90-degree thing is absolutely critical, right?
Right.
All
That's
nodes
exactly right.
relate at 90 degrees
Exactly.
on their own plane, on a one-dimensional plane at least. I don't know, very interesting. Okay, here we go.
You can see how the
We're on
self,
page
the
138.
yeah, the self-assembly works.
Yeah, and this is how self-assembly is working.
Exactly. That's exactly what it is. We start with the simplest case, two identical pairs of tangent spheres parallel to each other and separated by some distance. Rotate one of the two ball sets 90 degrees, and then move the two pairs toward each other until they meet in the middle, so that the midpoints or tangency points of the two pairs are as close together as possible. Notice that without the 90-degree twist, the result of bringing the parallel pairs together would be a square, unstable and not close packed. What is the result of this simplest case of interprocessing? A tetrahedron, of course. Go back up for a second. I just want to see something. Hang on 1 second. Oh yeah, okay. All right. Never mind. I hope I said tangency. Too close.
What makes the
packed
planets in my vision? Well, I think what makes the planets is the fact that these two objects are at 90 degrees with each other,
Yeah.
but they're able to maintain, they don't move closer together because of the angular momentum, the spin of these items, and how fast they're spinning and what direction they're spinning in and how fast they're moving out of orbit, which maintains, that angular momentum of the planet keeps it in its orbit around the sun because the sun's trying to suck it in, but it's speeding away. And so it
Right.
stays around an object. So in my brain, I was just creating a solar system. She's creating a close packed tetrahedron. Okay.
Too close.
That's my mumble. Anybody else want to chat?
No,
Or we continue reading?
no, we can continue reading, but it's starting to come together. It's really helpful actually how she breaks each one of these down.
Now, she says two close packed
pairs of spheres
creates a tetrahedron because here's two balls here, here's
Right.
two balls here. They're at 90 degrees with each other, but when they come together, they nest.
Yeah.
And when they nest, they create a tetrahedron. Blowing my brains out.
It's so much better than the way of describing it.
Wow. 817 is mind-blowing. Richard, you tend to be kind of quiet. Are you coming up with anything there? Or shall we continue to read?
No, how about we can continue? No, what I was doing is going back to the vertical axis and precession that creates motion 90 degrees to the axis. So I was just creating a model in my head actually on paper, that shows how the axis can then create a precessional movement sort of negatively at 90 degrees or positively. And
Right.
I was just relating it to the nature of our work and how I can take a vertical between a person who is having trouble wondering whether life is worth living, and they get into an axis with a helper, and the helper can either support them in going to the negative, to so at least talk about it, or support them processionally going to the positive and looking for ways to support that.
So they can either create, if I'm hearing you, they can create a negative tetrahedron or a positive tetrahedron.
Yeah.
Mm. Yeah, I've got something else going for me. I'll share in my takeaways, but this is, I mean, honestly, this is,
No,
you
it's
got
very.
you got four spheres in 90-degree relationships with each other on an axis. And when they come together, they don't form a square.
Right.
Because of angular momentum and spin, they rotate on each other and glow into close packing into tetrahedra.
Mm-hmm.
Whoa. That's why there are no squares unless you stick that sphere in the center of that thing and it pushes it out and creates the ability to create a square. And that square, if I remember right, is half of an octahedron. It's a pyramid. It's an Egyptian style pyramid.
Mm-hmm.
Well, I'm mumbling, but I hope that makes sense. And if I'm wrong, please wake me up. Okay. Shall we read a few more
No,
minutes?
I mean, yeah, just pausing on what you just said. If you, on that diagram, if you add one more in the bottom, you get 4, then yeah, you've created half an octahedron, and you've created a square-based pyramid.
Hmm. Is that?
Is that right? Yeah.
Yeah.
I don't know.
Because those
Yeah, because
3
there's
then
4
turn
around the
into a
base.
square.
They automatically turn into a square with
Yeah.
that
Okay.
center ball. That was in the previous drawing.
Yeah.
Here it
No.
is up here. Let's see. This is on page
But
137.
the word you just used there is the really important word. Automatically.
Right here. There it is. See, there's the one ball on top of the tetrahedron. There's the fourth ball. You start out with a tetrahedron, you add a fourth ball, it becomes half of an octahedron. Oops. No, that's still a tetrahedron.
Right.
3, 1, 2, 3. Oh, because we didn't add one ball, we added 3 balls.
Right.
Yeah. But if you add one ball, it becomes a half of an octahedron. Okay, I'm sorry to be so.
Yeah. No, it's, and
I mean, this is a
4
kind of.
becomes 5 balls.
Takes a lot of balls to do this
Yeah.
stuff.
A lot.
Okay.
Yeah, that's pretty good.
Yeah,
Okay. 2 last spheres.
I'll read for a bit.
Okay.
In retrospect, the answer appears obvious for the initial condition of 4 spheres. The necessary ingredients for a tetrahedron gives it away. However, the experiment highlights the 90-degree symmetry of the tetrahedron. Wow, that is powerful. Because, I've seen the 60-degree relationship in a tetrahedron, and this is now highlighting the 90-degree symmetry in a tetrahedron by simply looking at this graph up here. There's the 90-degree symmetry in the tetrahedron right there. And when it comes down here and these nest onto this guy, there's 2 90 degrees. Wow, how exciting. Okay. Oh, and then she even brings up the 60 degrees here. However, the experiment highlights the 90-degree symmetry of the tetrahedron, which is otherwise obscured by the predominance of triangles and 60-degree angles. I just said that.
Mm-hmm.
Rather than elaborating on the tetrahedron's right angle symmetry here, we shall allow subsequent demonstrations to further illustrate the orthogonal characteristic. See especially chapters 9 and 10. Take two identical sets of 60 spheres, close packed as shown in figure 818, which is on the next page. Their irregular trapezoidal shape eludes immediate identification. That they do not seem to be a part of our familiar group of shapes is confirmed by numerous experiments in which participants are given these two pieces and asked them to put them together in some way that seems correct. Countless false moves involve bringing similar faces directly toward each other, and again, the identical halves are put together in unsatisfying and incorrect ways. Tetrahedron as chef's hats.
Yeah.
Cool. Any comments on any of that?
Not yet.
Yeah, I feel lost about it, actually. To me, this looks like this thing upside down. I don't know. But I'm not sure because it's a different angle of the same thing. It's going back and forth. What is the question mark? Ah, I totally agree. Okay, the correct solution is rarely discovered by the uninitiated, but once seen, it is unmistakable. This problem, simple after the fact, is initially challenging because it is so hard to get beyond the natural assumption that two halves must approach each other directly, as if one half were approaching its own reflection in a mirror, when actually, what actually has to occur, of course, is that one half rotates 90 degrees and with respect to the other interprecessing, and the two rectangles mesh together perfectly at right angles. Wow, Bucky would exclaim, apparently as surprised as his audience. The surprise is genuine in a sense, for the result is visibly striking, even if one already knows the answer. A perfect tetrahedron, 8 balls per edge, or 7 frequency. And here's comes our next picture, 819. There it is. Chef's hat back to tetrahedron. Great. And we're at 10:48. We've only got 10 minutes. There's 3 of us. Probably we can leave right there. And let me see. Yeah, because she continues to evolve this thing for a little bit. So if everybody okay, we complete our reading now and just share our things.
Yeah.
All right, really good, because it is, after all, about 1 o'clock there, Joe. So
Yes,
Joe,
it is.
in this late hour, how are you feeling and what are your takeaways?
Feeling pretty good. It's been the end of a long day, but no, that I think kind of breaking down the shapes the way we have been, specifically even the tetrahedron, has actually kind of given me like a better way of explaining it. I still have to actually just sit with it a little bit. But I guess it's this idea, the thing that I was talking about a little bit earlier, and I mentioned a little bit earlier, was the self-assembling was definitely the most interesting thing for me this evening. Just how essentially how things fit together through nature, and how there's the relationships between the self-assembling structures, if you will, and how sound they are, I would say, structurally. Because you think about the jitterbug, and it's not only that it's when you unfold it, it's also sound, but it's also fits together, and so that kind of brings that into perspective. But there's the other aspect of it. It's just everything we're talking about here actually makes things more economical. That's the real key, is that you're maximizing the use of space, and when you think about it from that perspective, you can start to see how this fits into some of Bucky's other ideas, in the sense that you're doing more with less. So the idea that you're using space in a way that's actually more economically efficient, you're able to actually spot patterns and actually use and see how things fit together and understand what minimum structures are while they're still structurally sound. That has a lot of implications for systems. Um, and yeah, I mean, I'm still putting my thoughts together. That's a little disjointed, but one of the things that I have been taking away from this whole entire section of the book has been the efficient use of energy and space, and how she's walking us through, Amy's walking us through putting pieces together so that we actually understand the structures themselves and how they work from the inside and the outside. So yeah, anyway, it's also interesting in the terms of, I will say one more thing. If you're building a house, how you're minimizing the materials that you're using. And if you're minimizing the materials that you're using, then you're obviously doing more with less. So a lot to go on here anyway, that I'm taking away. Richard, how do you feel and what are you taking away?
Well, pretty good in terms of having been away for a couple of weeks and getting re-energized into these kinds of discussions. But I guess the thing I'm taking away is that transition from the cube octahedron squares over into the vector equilibrium triangles that create the icosahedron and its 20 triangles. And just to see that sort of natural transition from the squares to the triangles, and more I'm becoming comfortable with the importance of triangular stabilization, and that transition from the squares over to the triangles brought me back to the exercise that Bucky pointed out to the kids that he interviewed with and were written up in the book Bucky and the Kids. And he was trying to show why square tables are less efficient than triangle tables, and made the case that man always figures things out the hard way, and nature usually figures things out the easy way. And he used the square tables and the triangle tables to illustrate that the square tables take up more space, more area than the triangles do, and yet both give you the same answer. So why wouldn't we be teaching the triangle tables in school instead of square tables? And that's always been a mystery to me. But also, I know that when you talk about triangular structures like a geodesic dome or geodesic homes, you have most people sort of kind of go yuck at the idea of living in a floor of triangles or a space of triangles than a space of squares. So it's quite a transition, I think, for us to make the kind of move that Ariel is talking about in terms of the self-assembly of habitats. And the other thing that it brings my mind is the homeless village that was in Los Angeles in the 90s. And it was geodesic homes, and it was set up in such a way that if you had mostly single men living in the homes, you would have these separate little units. But if you had families start to come in, you can change the modular nature of the units into a family unit rather than just a single person unit. And how easy it was to be able to move triangular structures around in order to give you the flexibility of the kind of population that you're trying to serve. So I just taking out of this, along with other readings that we've done, is the more and more appreciation for what it is that Bucky was instructing or trying to get us to all sort of appreciate and understand. Yeah, so that's my big takeaway. Steve, how are you feeling? What's your takeaway?
Well, I'm feeling a little bit frustrated because I thought it was going to be easy to find. What was the name of the lady that Anne introduced us to that talked about the structures, self-assembly structures? What was her name?
Ariel Ekblom. No, no, Ekblaw, Ekblaw. And I looked it up too on another computer, and there's a couple of little YouTube presentations on self-assembly.
I looked for self-assembly. So Ariel, how'd you spell the last name?
Ekblaw.
Okay. Okay, there we go. Oh, funny, it doesn't put her name on it. At least the one that I've got here. Totally weird.
Oh, she's at
Oh,
MIT.
there's Ariel Waldman. And then self-assembling space structures doesn't give her credit. Artist animation, tesserae, habitat, self-assembly, and orbit. Well, so I'm not going to be able. It's what?
That what you just mentioned is tied to her work, and there's a video on that, and there's another video with her name that says self-assembly space architecture.
Okay, I'm going to take out space architecture. Sorry for that I'm so slow. Texture.
Self-aware assembly for space architecture.
There it is. I got it. And that's her. And I think I put him in last time. I will, as soon as well, let me just grab him right now while I've got him. Share. And got that one copied. Here it is in the chat. Lamo. And then you found the Wikipedia one. That's cool. And I think I got that one up there. So here's this one. And yeah. All right, good. So there's the two, I think, Richard, that you mentioned. They're both in there. And then Joe, you found another one too. So that's cool. All right. This has been really good for me because I just got back from Vipassana, and I mentioned earlier about the ice skater who's spinning and how the more dense the configuration is, the faster the spin, and the less dense, the less fast it is. But what I also realized that that's a skater who happens to be a solid biological being. And when in terms of energy, like a hurricane, the inside's going to spin faster than the outside. And it's not just based on the fact that because you would think if this thing is tethered to this center point and it goes around, it's got much further to travel out here than it does in here, but it would go the same speed. In reality, this thing goes way faster and kind of drags this behind it. That was the vision that I got. And I've before pondered the 90-degree relationship in a tetrahedron. And I think that what I got out before is very similar to what we just talked about, but this idea of having four balls, two in one relationship and then two in another relationship, and how they maintain that relationship as they come together. Instead of maintaining a square, they nest in and create the tetrahedron. and thus 90-degree relationships are maintained even though 60-degree angles seem to be present, which is interesting to me. Before I've discovered, like, here's a tetrahedron, and what I started looking at was at the edges rather than the balls. And what I noticed was that there's a 90-degree relationship, there is a 90-degree relationship, and here is a 90-degree relationship. And I think that correlates specifically with this idea of the twisting balls, but I haven't figured out yet for sure, but it's just brewing around in my brain over there right now.
Pretty cool.
I love the idea of the platonic solids not being solid. Richard reminded me of the framework idea that we've talked about in advance. And I'm delighted that you shared event foci, planar facets, and wavy linear relationships. I like wavy linear because when we talk about lines or edges, it's easy to imagine them being somehow straight lines. And as I've said before, there are no straight lines. And I even visited Richard's H pattern, which maintains the 90-degree relationship, but the interrelationships, that's not visible. The 90-degree is not visible. What's visible is the other interrelationships that go around those two spheres. So this has been a really good one for me. My frontal lobe is, I'm excited because at times I was lost, but at times I got it. And it's been really good for me. And I love the fact that I'm thinking about a gyroscope and then she talks about a gyroscope. Whee! So, it kind of means I was on some kind of track, probably just enough of a track to be dropped off in the South 40, but I was on a track. So I'm real thrilled. I'm delighted to be back in the saddle with you guys, and I'll be here next week. And I'm complete. Any other shares before we terminate the call?
I'm happy to have you back, Steve, and
Well, great, thanks.
both you guys. It's good to have you all back. And yeah, the only thing I'll say is that actually this has kind of awakened me a little bit. Now I'm gonna have problems falling asleep.
Well, let's hope that you can fall asleep when you get going.
Yeah, I know. I really do need it. It's like it but it's interesting. I've been kind of, but this past
Yeah.
this past 45 minutes, it just has gotten me up a little bit.
Oh, cool. Richard, you're not on Eastern time. Are you on Mountain time with me?
Yeah.
Yeah, so we're on the same time. And poor Joe is 2 hours. It's 1:30. It's 1 o'clock there. So
Yeah.
Joe, please take a big deep breath and sleep well, my friend.
Absolutely. Appreciate it, guys.
Thanks for making it. I'm glad Ann was here
Right
while
on.
she was here, and we'll see you all soon.
Take care.
Your
Bye-bye
weekend.
all.